Let's talk about the beautiful and unusual number e. This is an approximation for the number e. It's roughly 2.718. E is used all kinds of places and all kinds of surprising places. It's probably, like I said, one of the most important numbers that you've never heard of. Sometimes it's called Euler's constant. And yes, this is pronounced Euler. It's also known as the constant of growth, in part because we find it in nature all over the place, and there's a great YouTube video about that. But it's also used in finance. Like I said, it's used in nature, it's used in probability theory, it's used in the wave equation. Like the number pi, it is an irrational number, which means it does not end and does not repeat. But it still pops up in all kinds of crazy places. Let's talk about how to use it. We want to find the value of f of 4 when f of x equals e to the x. This is function notation, and what it means is whatever number is in parentheses here is the input. So asking to find f of 4, what that means is that wherever we have our input value of x, we just write the number 4. So essentially, this question is asking us to find e to the 4th power. We can do that on a scientific calculator. You should have a button that looks like this. So this is e to the power of. So if you type that and then type the number 4, you should end up with 54.598150003. There should be something in the directions about what number to round to. Frequently, we round to either 3 or 4 decimal places. So I would say, let's round this one to 3, just because I'm being arbitrary, and that would be our answer. Let's graph using e. I want to graph y equals e to the x power. So I'm going to pick some values for x and calculate the y. So I'm going to start with some negative numbers, -3, -2, -1, 0, 1, 2, 3, and we'll see what this looks like. When evaluating this exponential equation at x equals -3, what I'm going to type in my calculator is I'm going to type e to the -3 power. This is approximately 0.049787. It goes on from there. That is far more accurate than anything I'll be able to graph. I'm just going to round to the nearest tenth in order for me to have that would be 0. Let's round to the nearest hundredth, 0.05. The next one, I'm going to plug in -2 for e. Y equals e to the -2. Which is approximately 0.13533, and so on. So I'm going to round that to the nearest tenth and say that's 0.1. I'm going to do the same thing with e to the -1, which is approximately 0.3678. So I'm going to round that to 0.4. When I plug in 0 for x, remember anything raised to the 0 power just equals 1. When I plug in 1 for x, that's e to the 1st power, which is going to be that 2.71828. So I'm going to round that to 2.7. When we plug in 2, I end up with approximately 7.4. When I plug in 3, I end up with approximately 20.1. So graphing this, when x is -3, my y value is super tiny. When x is -2, my y value is tiny. When x is -1, my y value is almost up to a half. When x is 0, y is 1. When x is 1, y is 2.7. When x is 2, y is 7.4. That's just up there. And then when x is 3, 20.1 would be way off my graph. So our equation looks like what I hope you recognize is a very classically exponentially increasing curve. One of the reasons we care about the number e is because it brings in another form of the exponential equation. The one that we talked about earlier is this one right here. P of t equals some number, so an initial value, times b to the t power, and b can sometimes be thought of as 1 plus or minus r, where r is the growth rate, b is the growth factor. And we use this first equation when the change is either discrete or delineated. So what I'm talking about there is when we're told that the number triples every 3 days or something like that, or when the increase is changing by 5%. That's when we use this P of t equals a times b to the t power. There's a lot of applications in finance, in population, anything where the change is plus or minus some percentage. However, another way of writing the exponential equation is instead of writing our base b, we have this e to the r power. R is still the growth rate, but e to the r is the growth factor. And this is useful when we're talking about scientific applications like doubling time and half-life. I have no examples here, but we will be seeing this again soon. Thank you.